In this video, we're going to talk about rational exponents. Before we get to the rules, let's take a warm-up. Simplify x squared to the third power. When we simplify x squared to the third power, this outside exponent says we're going to write whatever's inside that parentheses that many times. So we wrote with it 3 times, and if we simplify it, we could. No, x squared is really just x times x. We could rewrite it so that we only have x's and all the exponents are away. 1, 2, 3, 4, 5, 6, and then we have x to the 6th power. So x squared to the third power is x to the 6th. But something to notice about this arrangement is that if we multiply together 2 times 3, it will give us 6. This is not coincidence. This is one of our rules for working with exponents. We notice a pattern that if I write out what's inside the parentheses or what's getting the exponent, and I've got another exponent, it will always turn out to be a multiplication. But what did we do to simplify? Well, the quick way is to multiply. We multiplied the exponents together. And so far we've only worked with whole number exponents. What if the exponent's a fraction? X squared to the 1/2 power. What should we do? Does it make a difference here compared to the first one? Should I try multiplying again? Let's try multiplying. Let's multiply 2 times 1/2 and see what happens. X 2 times 1/2. Well, 2 times 1/2 is the same thing as 1/2 plus 1/2. And if I have 2 halves of a pizza, I have a whole. So multiplying the exponents together, I get x. Okay. What do I notice about that answer and this one? Square root of 4, which is the square root of 2 squared, is 2. We already talked in our last class that the radical and the exponent cancel each other out if they're the same. If the index and the exponent match, they can cancel. And also if the index and the exponent have common factors, they can also cancel. But we're getting a little off topic there. The thing I notice is when we cancel the radical with the exponent, I'm just left with 2, but that's my answer. And up here, when I multiply 2 and 1/2 together, I'm left with just x, which was being raised to those exponents. So it's like the 2 and the 1/2 are canceling each other out, like the square root and the exponent down here. And that's exactly what happens. We can define rational exponents as roots. If n is an integer greater than 1 and a is a real number, then a to the power 1 over n is equivalent to the nth root of a. And just as with radicals, if we have even roots, if n is even, then a to the power 1 over n is not real. Looking at some examples, 25 to the 1/2, that 2 in the denominator of the exponent means we're taking a square root. And we can do that. The square root of 25 is 5. Same thing with 144, that 2 in the denominator of the exponent means we're taking a square root. Square root of 144, 12. Here we have a 3, cube root of 27, cube root of 27 is 3. Square root negative 16, oops, we have a negative number there, not a real number. And then 16x to the 1/2, square root 16x. We talked in a previous lesson how the radical plays nicely with the multiplication or division. So we can take the square root of 16 to get 4, but we can't do anything with that x because we only have one x and we're taking a square root and we don't know what x is. So we'll just leave it under that radical 4 square root x. We can expand on these rational exponents by not just keeping that numerator at 1, but having other denominators as well. If n and m are integers greater than 1 and a is a real number, then I have a to the power m over n is equivalent to the nth root of a to the m, but that's also equivalent if I switch the order and take the nth root of a first and then raise it to the mth power. All of these mean the same thing. And again, if n is an even positive integer and a is negative, we get that same situation that a to the power m over n is not real. Some examples here. 25 to the 3/2 power. We can look at this as, I'm going to take the first way, square root 25 to the 3rd power. Oh dear, I cannot do that without my calculator. I know 25 squared is 625, but multiply by another 25, that's really hard. So let's switch it around. These things are equal. Nth root of a to the m is equivalent to the nth root of a raised to the m power. So we can change it and say 25 square root first and then raise it to the 3rd power. This is a lot easier to deal with. Square root of 25 is 5. Oh, I know that. 5 cubed, that's 125. I can do that. Try 64 to the 2/3 on your own. Pause the video. Try not to use a calculator except to check your work. And then resume, and I'll have the answer for you. 64 to the 2/3. 3 on the bottom means we've got a cube root. And then we're going to square it. I like doing it with the radical first and then the exponent because the radical brings that number down to a smaller number that I can work with. Cube root of 64 is 4. 4 times 4 is 16. I skipped the exponent rules in the beginning, but hopefully they refresh your memory as to what is allowable with exponents and how the operations turn into equivalent operations. Now take these rules of exponents. They all apply to rational exponents and radicals. Know how to use them. So try it out on 1 through 4 with the 25. Pause, work them out, and then come back. We've got a square root. Square root of 25 is 5. Another square root. Square root of negative 25. I can't do yet. Here I've got 25 to the 1/2. I'm taking the square root first and then tacking on the negative. So that's a negative 5. The negative's on the outside, not underneath the radical. And then for 4, another square root, 25. But this time I'm raising it to the 3rd power. Excellent. Let's get a little more complicated and work with these rules. This is going to take some practice, and there are multiple ways that are correct mathematically that you can use to simplify these rational exponent expressions. So do keep that in mind. You can apply the rules in a different order and get the same result. In some cases, you can do something slightly differently. As long as we're using good mathematical practices, we should be getting the same answer. So if I do something different from you in these next sections, don't fret. See it all the way through and look if our answers match. See if you can determine what I did differently from you, if I did something differently, and why we ended up with the same answer. In number 5, I have x to the 6th over 27, all to the 2/3 power. I like doing the roots first, so I'm going to rewrite this as the cube root of x to the 6th over 27 all squared. This rational exponent here can be translated back into a root. So now I'm looking at the cube root of x to the 6th divided by the cube root of 27. I could look at it that way. But instead of converting it to the equivalent radical expression, which I could, let's work with the exponents and see if we can gain some insight there. Let's work with the exponents just like we would if they were whole numbers. Here I have something raised to a power, and I'm looking at my exponent rules. I have an expanded power rule for one thing, but I have an expanded quotient rule here where I'm dividing by something and they're both being raised to the same exponent. I want to apply the expanded quotient rule on this. Essentially, it's like a distributive property. I distribute that exponent to the numerator and to the denominator. X to the 6th to the 2/3 divided by 27 to the 2/3. And now that I've kept it in exponent form, I've got an exponent raised to an exponent, and I need to multiply them. 6 times 2/3. If I multiply these together, 6 and 3 have a common factor of 3. So I divide out the 3, and I get a 2 left behind on the 6. 2 times 2 is 4. So that whole piece becomes to the 4th power. 6 times 2/3 is 4. And then I can do the denominator, 27 to the 2/3. Now I can change it and simplify it. But I have this whole number here. Cube root of 27 is 3. 3 squared gives me 9. X to the 4th over 9 is my final simplification. In number 6, we could distribute the negative, but I'm noticing that my exponents inside the parentheses, I don't have negatives on them. So what if I use the negative to take the reciprocal? The negative exponent rule, that's exactly what it does. We take the reciprocal and we flip the fraction. So the negative here, I'll switch them around. Y to the 6th over x to the 3rd. And now it's to the 1/3. And then I can distribute it in. I've gotten rid of that negative exponent. We do have to be careful with those negatives. I like to think of a negative exponent as meaning the expression that has the negative exponent, it's on the wrong side of the fraction bar. So it needs to go on the right side of the fraction bar. Since this negative applies to the whole fraction, we flip the fraction. The negative up here in the rules, you see we have the negative exponent on the x, but that means that this expression, x to the minus n, it's on the wrong side of the fraction bar, so we switch it and we put it on the bottom. When we do that, we don't leave behind 0, we leave behind a 1, so make sure that that is made. The other thing to point out, a negative exponent does nothing to the expression as far as whether the expression is negative or positive. The negative exponent is just a notation to indicate a reciprocal. If you want a little bit more about negative exponents as far as the why it happens, we can do a really simple one. Let's look at powers of 2. 2 to the 3rd power is 8. 2 squared is 4. 2 to the 1st is 2. 2 to the 0 power, I'll actually leave that one as a blank. And then we'll look at 2 to the minus 1 power, 2 to the minus 2 power. Remember that math is all about patterns. So if I look here, to go from 8 to 4, I would divide by 2. To go from 4 to 2, I would divide by 2. To go from 2 to whatever should sit there, if I'm following the same pattern, I should divide by 2. 2 divided by 2 is 1. This is why any number to the 0 power is 1. And I continue the pattern. Divide by 2. 1 divided by 2 is 1/2. Divide by 2. 1/2 divided by 2. Oh, this is getting a little bit more complicated, but we can write it to the side. 1/2 divided by 2. Copy, dot, flip. There's that 1/4 that goes for 2 to the negative 2. And hopefully that helps think about what a 0 exponent means and what that negative exponent is referring to. Back to number 6. We can distribute that 1/3 to both the numerator and the denominator. And we do that y to the 6th to the 1/3, x to the 3rd to the 1/3. 6 times 1/3. Multiply it out. 6 times 1/3 will give you 2. And then 3 times 1/3 gives you 1. Y squared over x is our answer. A few more on the bottom for you to practice. I do want to look at number 9. I'll leave 7 and 8 for you to work on your own and check your work. In number 9, this one is a little different because now we have radicals. We have radicals in 8 as well. In order to simplify a double radical like this, we need to convert it to rational exponents. So I will attempt to do that now. X inside. So I've got the 4th root of x, and then I'm taking the square root of that. I can erase the inside parentheses because it's just an x. And then when I get exponents together like this, an exponent raised to an exponent means I multiply. And when I multiply these two exponents together, x to the 1/4 times x to the 1/2, we get x to the 1/8, which is equivalent to the 8th root of x. I can take multiple radicals, convert them to rational exponents in order to find the appropriate index for a single radical.